Hey everyone, and welcome. So we live in a world that is just overflowing with digital files, right? But have you ever really stopped to think about whether you can trust where any of them actually came from? Well, today, we're diving into a protocol that was built to answer that exact question with a solid yes. This is our deep dive into frozen trace fabric.
I mean, it's a huge problem when you think about it. You get an image, a document, a piece of code, and its history? It could be totally lost, maybe even forged, or most of the time just completely unknown. That uncertainty is exactly what we're tackling today, and the key idea behind the fix is something called digital provenance.
So, digital provenance, what is it? Honestly, the best way to think about it is like the ownership history of a famous painting, or the chain of custody for a piece of evidence in a court case. It's the whole verifiable story of a digital file's life, from birth till now.
And that is where frozen trace fabric, or FTF, comes in. At its absolute core, it is an append-only protocol. Just picture a captain's logbook. You can only add new entries to the end. You can never, ever go back and erase or change something that was written yesterday. And that super simple rule, well, that's the foundation for everything. It's how you build a permanent, provable history.
Okay, so let's dig into that foundation. This whole idea of an immutable, meaning unchangeable ledger, this is really the first layer we need to peel back to get how FTF builds trust from the ground up.
The whole system is built around just a few simple verbs that describe basically any action you can take. You can put a new file into the system. You can exform it, like say, you compile some code. You can attest to its quality or revoke an older version. The trick is, every single one of these actions gets recorded as a signed message. It's just another permanent entry in that logbook. And right here, this is the most important part. Every single one of those actions, signed by whoever did it, just gets tacked onto the end of a list. That's it. There's no fancy database, no backdoor to sneak in and edit an entry from last week. The history just grows, one entry at a time. This append-only design is the bedrock of the whole system's security.
So you might be thinking, okay, if it's just a simple list of messages, how in the world do you get a rich, structured history out of that? And this, my friends, is where the magic happens. It's called the deterministic replay engine. The whole process is completely 100% predictable. Anyone, on any machine, anywhere in the world can follow these exact same steps. You read the log, you verify every single signature to make sure nobody's faking anything, you sort all the messages based on one strict rule, and then, boom, you project that sequence into a complete history. Because the steps are so rigid, everyone gets the exact same result, every single time. And what is that one strict sorting rule? It's this beautiful, simple two-part key. You sort every message first by its timestamp, and if two messages have the exact same timestamp, you use the hash of the message itself as a tiebreaker. That's literally it. This guarantees that no matter what order the messages came in or how your computer feels like storing them, the final history is always sorted into the exact same stable order. The protocol's own design documents call this out as a core invariant, basically a non-negotiable promise. The replay order is deterministic and stable. That's not a guideline or a suggestion. It's a mathematical guarantee that's baked right into the heart of the system.
All right, so we've got this stable, predictable history, but how does it all fit together? Well, the beauty of FTF comes from its super clean three-layer architecture. It's like a blueprint for building trust. Way down at the bottom, you've got the identity layer. This is all about cryptography. Every single message is signed with a private key, which creates a public signature. This layer's only job is to answer one simple, powerful question: who said it? Sitting on top of that is the replay layer, which we just talked about. This is where that timestamp message hash key does all its heavy lifting. It takes all those signed messages from the identity layer and arranges them into that single official timeline. Its job is to answer the next question: in what order did they say it?
And then finally, at the very top, you get the lineage layer. This layer takes that perfectly ordered sequence of events and actually builds it into a meaningful graph, a story. It connects the dots, showing how this file was used to create that file. This is the layer that finally answers the big question: what story does this whole sequence tell?
Okay, but what happens when you make a mistake? We all do. Or what if you want to endorse something? If you can't change the past, how do you handle corrections? This is actually one of the most brilliant parts of the design.
See, in a normal system, you'd probably just go back and edit the record, right? You'd rewrite history. But that totally destroys the audit trail. FTF works more like a really careful accountant. You never, ever use an eraser. Instead, you add a new entry to correct the record. The original history is preserved, and you just add more context.
So the key takeaway is that attest and revoke aren't edits at all. They're just new signed messages that you add to the log. An attest is like sticking a post-it note on a document that says, hey, I checked this, it's good to go. A revoke is like adding another note that says, whoops, correction, that thing I said before was a mistake. The original record is still there untouched, but now everyone sees it with that new context. Now, the real payoff for having this super strict, small, and stable design is just enormous. Because the core protocol is frozen, it becomes this rock-solid foundation that you can build all sorts of amazing things on top of. And this quote from the design rationale just says it all. The philosophy isn't to just keep cramming more and more features into the core protocol until it's a bloated mess. No way. The goal is to keep that core tiny, stable, and easy to audit, and then build new tools around it. And here are just a few examples of what that looks like. You can build spaces, which are like managed workflows for teams. You can build federation, which lets different organizations securely connect their histories. You can create new transport layers to share these logs around. And you can do all of this without ever having to change the fundamental rules of that frozen core. So when you start connecting these different spaces, the number one rule is safety first. By default, your team's history is your own little island. My trace happening over in Space Alpha has zero idea what's going on in Space Beta. That's locality by default, and it's huge for preventing accidental information leaks. So, how do you collaborate? Well, you do it through a very deliberate, auditable action. If my team in Space Alpha wants to give a file to your team in Space Beta, we create what's called a handoff artifact. Your team then has to explicitly take that artifact and put it into your own history. The connection is totally intentional and recorded. It's not some magic behind-the-scenes thing. And all of these design choices, the immutable log, the deterministic replay, that clean layered architecture, and the frozen core, they all come together to create this one thing, a small, incredibly reliable, and deeply auditable protocol for establishing real, provable trust in the digital world. So I'll just leave you with this thought. Just imagine a world with no more mystery meat software, where you actually know where your code came from. Imagine a world where the source of every news photo is verifiable with a click, where the data behind a scientific paper has a permanent, unchangeable trail. What else becomes possible? When every single digital thing has a history you can actually prove?